Okay, can I start now?
Yes, sir. Sir, Assalamu alaikum, sir.
Walaikum assalam.
Assalamu alaikum, sir.
Walaikum assalam.
Sir, is there any possibility to have an extra assignment that we can do?
Assignment, I will not give any assignment. The reason is, if you give assignment, you copy, so it is not possible. But I try to take another class test. Okay?
স্যার আপনি কি স্যার ওই 3-1 এর মতো টাইম কনস্ট্রেন্ট দিয়ে একটা অ্যাসাইনমেন্ট দিতে পারেন?
কোনো রকমের কোনো টাইম কনস্ট্যান্ট দিয়ে হবে না, স্টিল ইউ কপি, and I have no time to examine such assignment. Okay,
Yes, sir.
so I will take another class test of this form that you have already appeared. Okay,
ইনশাআল্লাহ, স্যার।
another issue is that you cannot imagine that how much time it will take to examine, for example, your scripts. In your mid script, how many questions you appeared?
Sir, 4
Total altogether 164 into 4.
Yes, sir. Almost, sir, 700 questions, sir.
Around 700 questions. So do you think that it is possible for me, for example, to take such exam frequently? In other days, what we need actually, we have our same types of questions for our students, and we can take help of TAs. They will help us to grade or something like this. But no, nothing is there. Along with my other duties as departmental head, and many committees have been formed, and I become the chairman, and I have to write report. Many things are there. I am getting actually sick.
Sir, the thing is, sir, the time limit of the semester is, sir, very low, sir.
This is the reason that we started later, because we started late, and we want to do everything.
But we are getting 2 weeks. But we are getting 2 weeks less than a regular semester because of the time constraints.
This is for your benefit. It is not something like that we are getting any advantage from it. You are the one who will be the beneficiary of this thing. Because if you cannot start your semester, how will university run? Do you think that from where the teacher will get their salary, and how the university will run if they cannot admit students in January?
Yes, sir, I get that. But for
Yes,
our
sir, but-
quizzes, this is basically happening is like a binary marking. So
But your course and your other things have been shortened actually. Your exam syllabus is also have been made easy. In your final exam, you have to appear in all of your syllabuses, but now you need only after mid, and only 20% mark is there in written. So these things are made easy for you, although the time is a bit short. Okay,
Sir,
Yes, sir.
you have to get it. Yes.
Sir, most of us
sir,
did.
can we?
Sir, most
Sir,
of us did.
most of us did better in the mid than the quiz because it was a written exam and we could show our work, even if our result was not accurate. But if we could show the work up to a point.
I understand it, but this cannot be done, for example, for class test. Class test is MCQ.
Yes, sir. But can we shift some marks for the final then? Like
No.
For this semester, the quiz has more marks than the mid, even
That
the
you have to
final.
raise the question early when the things were circulated. This is not done by myself, okay? If you have this proposal, you contact with admission committee chairman who prepared this thing, okay?
Sir, then can we have an assignment? Because
Assignment, I will discourage the assignment. The reason is that my experience of taking assignment is awfully bad. And even whatever I have taken earlier, I will not evaluate them. The reason is that you have copied everything. I cannot encourage copy, okay? This is online and we are having a situation that is abnormal. You cannot expect, for example, everything that you enjoyed during your physical classes, okay? Because I cannot monitor you.
Sir, then can we have the quiz in online sessions like the Meet? Then there shouldn't be the issue of copying them.
Online quizzes like Meet means? Do you think that in taking these quizzes of this type, how many hours will be needed? Or how
No,
many
sir.
people should I have to involve? Do you have that luxury in class test? Because in final, you see, you have been categorized into 4 or 5, 6, around 9 classrooms. We have to engage 9 people there. Is it possible to take class test in this way? Although I have to take 4 or 5 class tests. What is the problem, for example, in your quiz that I am taking?
Sir,
Let me know it.
So the main problem is that this is the time constraint and the binary marking.
Time constant is not something like it is binary. MCQ type question is always binary. And if you have your idea, the questions are very tiny type questions. Okay, anybody can answer.
Sir, basically we are really not used kind of
What is
this kind of quiz.
what you have to use to it. You have to be.
Yes, sir, but that's why there is a huge difference between the Meet and the quiz, because in the quiz it's like that we can't even get 20% of the marks.
Quiz is usually taken by the teacher in whatever ways he like. Okay, so my quiz will be like whatever you have appeared. Okay, so it is you have to practice. I did not get any give any question there that needs huge mathematical calculation. Simple things are there. The reason is that you are not practicing and not engaged. So you cannot, for example, expect everything there, okay? As it is online, my questions are very tiny. And in that class test, many students are also getting good marks. So if you want to have your class test, then another class test I will be taking, like MCQ class test. And in MCQ type classes, you have your result already, guidelines are there, you can easily verify. If I take longer time, then you will communicate to each other.
Sir, it will be very much beneficial for us if you give us some type of math suggestions like you used to give us during the...
Just you follow the procedure that I usually follow in my class lecture. I have illustrated few things and you have seen that all things are there, something like this. But I have to set few questions to single out good student that you have to be careful about. Because I cannot make easy questions for all. In your physical class test, do you think that everybody get 50%?
No, sir. You set your question according to your choice, but we request you to give us some suggestions so that we can practice.
No suggestions are there. This is engineering education. You think will be there based on my lecture. So you follow my lecture, solve some representative problem that is there in your book. I hope you could solve every problem there. For example, in the last class test, what is the thing that I have given there that we did not discuss in the class? Can you identify one?
Sir, we solved all the book problems, but still...
All book problem cannot be there, because if I give the book problem, you will simply replicate the result. But they are similar to the book problem. They are very similar to your book problem.
No, sir. Basically, you used to give us some suggestions.
Do not argue in this way, because I will not take any other form of quiz, okay, rather than using this LMS, okay?
No, sir, not about the quiz. Basically, you used to give us some types of math that we could practice. So we could have...
You practice your math from your book. And the problem that you have found in your class test, are they different from that is there in your book?
Yes, sir.
For example, the one question was there, a Fourier series was there, and you have been asked whether it is Fourier series, Fourier transform. Is it not the question one of you from your book? Another thing was there, for example, Fourier transform of what we call some u minus n. Is it not a problem that I solved in the classroom? And an exponential form of Fourier series are there. Is it not from the example? So do not think that everything in your own way. So let me finish my lecture today. You try to download the question, then try to verify that how many of them are very similar to your text. Then let me know it. Because your exam is exam. You cannot expect that everything from your book will be replicated in your exam. So what we were discussing about in the last class about the properties of Fourier transform. One such property is a convolution property. That convolution property is this that we have discussed earlier. But we have two things there, convolution. One, a convolution operation in the time domain, it becomes a multiplication operation in the frequency domain. And you know this thing, this has wide applications in dealing with LTI. If we have a system LTI, then you know that an xt input is there and your impulse response is there. This is your output, yt. That I am discussing almost 100 or 1,000 times in my class. So your output yt is equal to the convolution of your input with your st. But if we want to convert it into Fourier transform, then your output yj omega would be equal to xj omega multiplied by hj omega. That is an operation in frequency domain, it becomes the multiplication, and in time domain, it is convolution. But we may have our operation multiplication in the time domain. And what will be the operation in the time domain? Just by exploring the duality property of Fourier series, even you can check it from your text that if we have, this is mathematics, this is not engineering. So it involves only simple integration type mathematics, nothing more than that. So if we have our product operation, say we have two functions xt, we are multiplying it with say wt, two functions are there. Then what will be the corresponding, say this is yt. It is not related to any input or output, just a multiplication of two functions in time domain. Then the corresponding frequency domain operation will be this. The convolution operation in the frequency domain, this factor is coming from the integration Fourier transform pairs. This is one important property. We will be using it later. Another important property is the scaling property. We have two scaling properties. One is amplitude scaling. Another is time scaling. If we have our amplitude scaling, then that will not affect the frequency spectrum of our signal. But if we have our time scaling, then you can easily verify that if your signal is time scale, then what will be Fourier transform? For example, if xj omega is the Fourier transform ft of xt, then what will be the Fourier transform of xat? Okay, you can easily verify it that Fourier transform of xat will be equal to what? It is simple, would be equal to minus infinity to infinity xat e to the power minus j omega t dt. You can change the variable at to tau, then you evaluate the integral, you will see that that integral will take this shape. That means you see that your amplitude will be scaled by the factor a, and your frequency is also inversely scaled. This means that if your a is greater than 1, a is greater than 1 means what? Your signal is stressed or compressed. Your signal is expanded or compressed in time domain.
Compressed.
It is compressed. If your signal is compressed in time domain, what is the effect in the frequency domain then?
Frequency increases.
That means frequency is expanded, okay? That we have already discussed for the case of a single pulse, okay? That we have seen that if we have a pulse, for example, with duration equal to minus t0 to t0 with amplitude equal to 1, this is your xt. And the corresponding Fourier transform is x j omega equal to what? X j omega was equal to, so far I could remember, 2 divided by sine omega t0 divided by omega or something like this. If this is used signal, you see that if your t0 is, for example, scaled by a factor a, and if your a is equal to greater than a is greater than 1, then what is happening? This thing will be coming here. As a result, what will happen? Your frequency, for example, initially your spectrum was something like this. Now your spectrum will be expanded, isn't it? So a signal cannot be consecutively localized in the time domain, or time limited and band limited, because if your signal duration is reduced, the spectrum of your signal will be increased. For example, if I want to set a problem regarding this in your quiz, okay, I will set a value of A or set a value of frequency, and you have been asked to find the value of the spectrum at a particular frequency. Is that problem needs, for example, any thing from your book? If you can follow this class clearly. So all the problems were of this type. Okay, this example is already I have discussed, okay, that you can easily look at it. That if we have our pulse with duration equal to minus 2 time unit extending from -1 to 1, and another pulse is there with this time, you will see that the Fourier transform of these two pulses is actually related to the frequency spelling. In the case of wider pulse, you see that your frequency spectrum is wide, is narrowed, and in the case of your shorter pulse, your frequency spectrum is widened. This is illustrated there. Now, this is very important relationship, although it is mathematically, but very practical applications in our signal and systems. Actually, this is the relationship of energy in time domain as well as in frequency domain. You see that this is it not the integral for energy? The integral, this one, is it not energy?
Yes, sir.
Actually, why we are using magnitude? Because to make it general, okay? You see that your signal can be complex. If your signal is complex, two signals cannot be multiplied, and it has no meaning in sense. For this reason, what we need to do, we have to multiply a signal with the conjugate of this signal. Then what will happen? This becomes the magnitude square, isn't it? So if we integrate this magnitude over time, it is the normalized energy of your signal. Now, if this is the energy in time domain, the left-hand side, your right-hand side is what?
Energy in frequency domain.
In energy in frequency domain, we can easily prove it. Okay, as you know that your xt equal to what? Your xt equal to 1 divided by twice pi integration minus pi to pi xt. No, not xt, because we are taking inverse of Fourier transform to calculate the energy. This is your x j omega e to the power j omega t d omega. Now, if we, for example, conjugate this thing, x conjugate t, then what will happen? The complex thing here in this integral will be conjugated, isn't it? And if you multiply them together, and you will see that this conjugation will result in an equation something like this. And this has been proved in your book, so have a look. This is simple integration and mathematical operation. Okay, but what we need to do, we have to apply this equation in our signal. Okay, what is the benefit of using this thing? Okay, two perspectives are there. One, your energy content of a signal will be transferred into transform domain. For example, this is your time domain. This is your time domain energy, and this is your frequency domain energy. You see that the energy content are same. This signifies that whenever we transfer a signal from one domain to another domain, the energy content will be remaining same. This is one thing. This is true for your Fourier transform as well as for Fourier series. Another issue is that will help us. This relationship will help us in finding the energy of some time domain signal that are a bit complicated, that has complicated form in time domain. For example, if we have a signal, say something like this, sine, say omega t divided by say pi t. It is a sync type signal. We know that the corresponding frequency domain will be what? Frequency domain will be, signal will be something like this, minus w to w with amplitude equal to 1. This is the frequency spectrum of that time domain signal. Now, if you want to calculate energy from time domain, what you need to do? You have to square it. Then you have to integrate it from minus infinity to infinity, isn't it? Then that will give you the energy in time domain. Okay, then equivalently, you can square xj omega, magnitude of xj omega, and you can integrate it. In this case, you see xj omega exists from minus w to w. Then within this range, you can complete your integration. This is your d omega. Which integral will take lesser time? In carrying out the integral, which one will take lesser time? The time domain one or frequency domain one?
The frequency one.
Because you see that in the wink of an eye, you can easily see that the frequency domain integral will give you the result twice w divided by 2w, okay, equal to w by pi, okay. It needs a second to do that. But can you do this thing in the, so simply when we start with time domain?
No, sir.
So this is what another benefit, okay. That, but in the reverse way, we can also go. That if we have a frequency spectrum, say sync type function, the time domain signal is a pulse, isn't it? So in that case, it is easy to calculate the energy from frequency domain. For example, say if we have a signal, say e to the power 80 ut, if someone will call you to just calculate the energy, what is the energy of this signal? It is simply 0 to infinity e to the power minus 280 dt, isn't it?
Yes, sir.
And equal to what? Is it not simply equal to 1 divided by twice a? That's so easy. But if you want to convert it into frequency domain, then xj omega equal to what? 1 divided by a plus j omega, isn't it? And magnitude of xj omega equal to 1 by square root of a square plus omega square. Then the energy again can be calculated by using this Parseval identity equal to 1 by twice pi minus infinity to infinity, and your equation is xj omega square, that is 1 divided by a square plus omega square d omega, isn't it?
Yes, sir.
Okay, in this case, you see which integral is a bit easier?
So the time domain.
Time domain one, okay. What is the value? Can you show that this integral will have the same result equal to 1 by twice a? What is the integration? Integration minus infinity to infinity 1 divided by a square plus omega square d omega. So this is math or engineering?
So mathematics.
This is simple math, okay. So
Sir, we can't hear you.
Can you see this screen?
Sir, you were muted. Now we can hear you.
Can you see this screen?
Yes, sir.
Yes, sir.
Did we discuss about this? So probably we have discussed this thing for the case of continuous time signal. Now this is your discrete time one, okay? You see that this discrete time signal is a sinc function. And it looks like this, okay? We have a magnitude there, something like this. I hope you can remember this, okay? We have dealt with this signal earlier, okay? If you want to calculate the energy, what you need to do? Here, do you need sum or integral?
Sum.
Sum, okay? This is simply magnitude of xn square, okay? Although many of you has this confusion also. So if you have this thing with you, how can you expect that they will do good in exam? They cannot differentiate between discrete time one and continuous time one. So this is your energy. And can you find that this sum so easily? Evaluate that sum so easily? It is very difficult.
Yes, sir.
But we know that the Fourier transform of xn is this. It is simple, okay? Something like this, from minus w to w. And you know that discrete time Fourier transform is periodic. So only one period from minus pi to pi is given there. So then you can easily integrate from minus pi to pi, minus w to w, 1 by twice pi square of your spectrum. This is equal to w by pi. So it is much more easier than evaluating this sum. In this way, your Parseval's theorem will help us evaluating the integral of this type easily. Okay, you have your problem there of this type from your book. Okay, try to practice the problem. And again, I need to reiterate that none of this problem will be replicated in any of your text, but the underlying theory will be applicable. So with this thing, because many other issues are also there, mathematical, I think in course of time, when you will be applying the thing in higher level courses, you will be getting accustomed to the process. Another issue is that although you have your lab going on, I don't know what you are doing in your lab, but I am repeatedly saying from your first year that at the end of the chapter of this book, there exist many, many tiny problems and MATLAB programs are there. You can easily explore the thing by simply rekeying the thing in your computer and exploring it. I don't know how you can do it. Okay, without practice, no matter how brilliant you are, thing will not work. So with this thing, let me conclude our properties. Then we will be going to applications. And I hope that in application-oriented side, we also need some theoretical thing. The reason is that if you want to use Fourier transform, then Fourier series can also be expressed in terms of Fourier transform. That thing will illustrate, then we will be discussing with some examples where we can use our Fourier series to analyze our system. Okay, let me share the whiteboard just to illustrate the process. Actually, what will be our process in our LT system analysis in transform domain? We know that our system is LTI because without LTI approximation, we cannot take nonlinearity there in the transform. So if we have our xt there in time domain, our signal system will have our st, the impulse response, then we obtain yt. This is what the time domain representation. What we have seen in our frequency domain, that if you want to use frequency domain, then your signal should be transferred into frequency domain. And your impulse response should also be transferred into frequency domain. This becomes your Hj omega. Then your output will be Yj omega. The Fourier transformed output is the multiplication of Xj omega into Hj omega. Then we can find our Yt by taking Fourier inverse of Yj omega. This is what the whole process. And you see that this output is actually ZSR, zero state output, because no initial value, because convolution operation is applicable for zero state output. Now the central thing is what? Your signal will be given, so you can use your technique there to convert it into frequency domain. Now, how about ST? Your ST can be determined by yourself or it will be given. In order to find your ST in time domain, you need the input-output relationship. Your input-output relationship for a continuous time system is an ODE type. And for a discrete time system, it is your difference equation, isn't it? So the input-output relationship for a continuous time system will be ordinary differential equation. The order of the equation depends on the order of your system. And for the case of discrete time, it will be this difference equation. In both the cases, we can directly find from ODE, we can find HT in time domain, and we can find HN in time domain. Then once these HT and HN are available, then we can convert it into Fourier transform in this way. This become Hj omega, HT become Hj omega by using Fourier transform equation. This is one way to do that. Another way is what? Another way is, we have other two ways actually to determine the Hj omega, because Hj omega is the main thing you have to determine first. In this case, if your system is there LTI, you transfer your system to frequency domain. How to transfer it? If your system is a passive system, eventually your frequency dependent element L can be represented by J omega L. Your C can be replaced by 1 by J omega C. Is it new to you? Because you know this thing from your first year. It is simple phasor conversion of a circuit. Then you can apply your circuit theorem there to find the input-output relationship and Hj omega. We have illustrated the thing earlier using a simple example. Or what you can do, where your ODE is available, then you convert that ODE will be in the time domain. Then you apply your Fourier transform there, FT. Then it will be converted into Fourier frequency domain. How? You simply replace your derivative by J omega. If it is a k derivative, then you simply multiply it with k. Can you remember this thing?
Yes, sir.
Then what will happen? If your input equation is of this form, say k equal to 0 to say some order, say m, and this is your ak, dk, dtk, y, then after Fourier transforming, it will be equal to what? Sum k equal to 0 to m, your ak will be there, your derivative will be replaced by what? J omega to the power k, and it is your y j omega, isn't it? So in this way, you can convert your signal differential equation
Just hold a second, please. Okay, is it clear? So in this way, your time domain differential equation is transferred into frequency domain, okay? But we have an input part also. In your input part, say this is m equal to 0 to some m, and your input part was say bm dd tm xt. If we transfer it into frequency domain, it will be equal to what? Sum m equal to 0 to m, it is bm j omega to the power m xj, isn't it?
Yes, sir.
Then if we, because xj doesn't contain anything k, so you cannot take this thing out of this sum, then we can easily find the output input ratio, isn't it? And that will be equal to what? H j omega, and that is equal to sum what?
M equals 0
M
to
equal to 0 to m bm
j omega to the power
j
m.
omega to the power m divided by sum, this sum, okay, ak j omega to the power k, isn't it? So in this way you can easily calculate or find the transfer function, okay. If you have your book with you, Alexander Sadiku's book, chapter 18 or 17, I cannot remember, where the Fourier transform applications are there. I will just simply give one, what you call, one illustration, okay, how to proceed with. This will not, for example, coincide with, say, any problem, but you will see that if you can remember the technique of handling this thing, you can easily, for example, proceed with solving any type of problem of this type. Okay, consider one. Oh, where am I? Can you see the slide? What do you call? Okay. Okay, consider that we have a circuit something like this. This is Vs. A resistance is there, say 2 ohm. Another resistance is there, say 1 ohm. And we have a capacitor there, something like this, say 1 farad. And if we apply a pulse there, say this pulse is 1 second duration, amplitude equal to say 10 volt, and this is your VST. And you have been asked to calculate the voltage across the capacitor, VCT. Okay, how many different ways you can go? You can derive the input-output relationship that needs the knowledge of first year. Then you can find, transfer it into frequency domain by replacing the derivative by j omega. Then you can proceed with finding your yj omega, that is equal to Vc j omega. Then you take Fourier inverse. This is one thing. Another issue is that you transfer your input into frequency domain. What is the Fourier transform of this pulse? Your VST can be written in how? How it can be written? With the help of unit impulse. Is it not 10 ut minus 10 t minus 1? Then if we take the Fourier transform of V j omega equal to what? It is what? Ten divided by j omega minus 10 divided by j omega. What factor will be associated with it because of this delay? Hey, if a signal we have xt, whose Fourier transform is xj omega. If we delay the signal from t to t0, what will be the Fourier transform? Okay, try to remember the thing from your earlier level. Okay, so when should xj omega will be available? Then what you need to do, you convert this circuit into frequency domain. Then this Vj omega would be equal to Vj. Your R will remain unchanged. And your C will be equal to what? And your output will be Vcj omega. And C equal to 1 farad. Then the corresponding impedance will be equal to what? 1 divided by?
J omega C.
Is it not? Okay, is there anybody who cannot determine Vcj omega by using simple potential divider rule or something like this? That's how you apply your first year circuit theory to find your Vcj omega. Once your Vcj omega will be available, then Vcj omega divided by Vs, that means the source, Vsj omega, would be equal to the transfer function of this circuit. Then you can take the Fourier inverse to find the transfer function. What I have told you earlier, that if we have a function, say e to the power at ut, its Fourier transform is what? 1 divided by a plus j omega, isn't it? Okay, tell me, if you have a function e to the power t, what is the Fourier transform? Or what do you mean by this function? Can you plot it into the time domain? This is there from your book. If you plot it into the time domain, this is your time. How the function will look like?
It will be exponential decay in both sides.
Isn't it?
Yes, sir.
Then how can we calculate the Fourier transform? You simply take the Fourier transform from minus infinity to 0, e to the power t into e to the power j minus j omega t dt. This is your first side. And the second side will be equal to 0 to infinity e to the power minus t into e to the power minus j omega t dt, isn't it?
Yes, sir.
Okay, look, this is a problem from your book. If I modify the problem by changing the t or giving an amplitude there, something like this, will it change, for example, the method that we are using to solve it? It will never change the method. So that the thing you have to be considered about. Okay, if you practice few things, you is automatically getting accustomed to it using this result. Now the thing is that this signal has a support from minus infinity to infinity. Okay, if we shift the signal, the 0 position will be shifted, but still your signal will be from minus infinity to infinity. But this type of signal, you see, has a support from t equal to what? If the plot is something like this, from t to say, this is your t-axis. Okay. Now, if we shift this signal somewhere, both in the positive and negative side, then what will happen? If we shift there, your signal will be coming in this form, isn't it?
Yes, sir.
Then what will be the expression of this signal? This signal will be e to the power minus e to the power a t minus 1 ut minus 1, isn't it?
Yes, sir.
But if someone will write it in this way, e to the power minus at ut minus 1, is these two signals same?
No,
These
sir.
two signals are not same. For this reason, actually, in order to apply the shifting property, you have to be careful about if we have a signal, for example, minus at ut minus 1, this signal shifting property cannot be applied directly. what you need to do, you have to express the signal in this way. A, we can write t minus 1 plus 1. Can we do that? And ut minus 1. And that will be equal to e to the power minus a into e to the power minus a t minus 1 u t minus 1. Okay. Then this signal is actually obeying the time shape. This is a factor there. Okay. Then Fourier transform, we know that Fourier transform of this signal is 1 divided by a plus j omega. Then what will be the Fourier transform of this signal? A delay factor will be coming here. 1 plus j omega will be remaining same. A delay factor j omega is coming. So this is what the Fourier transform of our signal. Then this factor was there originally. You multiply this factor there. Okay. So this is the Fourier transform. So you have to identify when taking the Fourier inverse. For example, if a function of this type will be appearing in the Fourier transform, the corresponding Fourier inverse will be equal to a delayed function, for example, something like this. But the original function will be the transform of original function will be remaining same. Only a phase factor will be multiplied with it because of the delay. In the case of frequency delay, what will happen? If we have a function, for example, e to the power j omega 0 t with multiply with xt, then that multiplication results in a shift in your frequency by omega minus omega 0. That will be needed in our few applications. Another issue is that whenever we are dealing with application-oriented problem, okay, why we need the properties? We can use the properties, for example, of Fourier transform to take the Fourier inverse of signal very easily. For example, say, if we have a function something like this, if someone will tell you to take the Fourier transform of this function, actually this will take time. But if we differentiate it, how it will look like? If we differentiate this signal, what is the shape?
Square wave type shape.
A square wave, something like this, isn't it? If we have this signal, which one is simpler to take Fourier transform?
The bottom one.
Bottom one. Then how can we go to the top one? By using the integration property. So in this way, your integration property and differential property will help you to find the Fourier transform. If Fourier transform is applicable, then rest of the applications are related to circuit theory or something like this. So try to solve few examples or problems from Alexander Sadiku's book to get accustomed to it. How can this be applied? Or if you have any circuit book that contains Fourier transform, you will find many applications there. Only one problem you can solve correctly, then you can solve many problems of this type. Now we will be going to Fourier transform applications chapter 4 of your book. And we will not cover everything, but we will be dealing with few important things that is needed in our case at this stage. Where is the... Can you see this?
Yes, sir.
So this is chapter 17 of your Sadiku's book, okay? And chapter 18 probably deals with Fourier transform. Okay. This is a simple circuit. And a current is given there. This current appears to be a Fourier series, isn't it? Is it not a Fourier series? Can you identify whether it is a Fourier series or not?
Yes, sir.
How to identify?
The cosine, the frequency is 3 times the
Yes, that is the important thing. Okay, that if the frequencies are integer multiple of the fundamental one to a relationship exists, for example, say higher frequencies are in omega, okay, would be equal to k omega 0, then k is an integer, then that belongs to the same Fourier series. So actually these belong to the same Fourier series, okay, and it is in the trigonometric form. If we want to express it into exponential form, how many constant will be there? Fourier coefficient will be there, because each cosine will generate 2, isn't it? So 2 is there plus 1 is there. So if we want to express this quantity as x, then we will have our x0, the coefficient correspond to this. We'll have our next is what? We can have our x, say plus minus 1. Similarly, we will have our x plus minus what?
2.
Is it 2?
3, sir.
Okay. Because you see in exponential form, your negative frequency will be appearing as conjugate pairs. Otherwise, real signal cannot be generated. So, in your first year, can you solve it by using your first year knowledge without taking Fourier transform? You see that your I has 3 constituents. One is a DC, another is an AC, say with frequency omega equal to 1 radian per second. Another is a frequency with 3 radian per second, isn't it? Then what you can do? If you want to use it in complex frequency or phasor domain, you cannot consider all these things together. You have to separately solve for DC. Okay, tell me, if we have DC 2 ampere applied, in the steady state, what will be the VT? If a DC current 2 ampere is applied to this circuit, what will be the voltage across the capacitor?
20.
It will be equal to 20 kg.
20
This
volts.
is what the problem with you. Okay, you guys are not suited for engineering education. Be careful about that. So it is 20 volt. Now, if we apply, for example, then 20 volt will be the voltage, number one. Say you can find that this is the contribution of this DC to this resistance. Now, if we want to consider, for example, the next source, 10 into cosine t plus 10 degree, what will be the corresponding voltage? That you cannot say so easily, isn't it? What you can do, you can use your phasor algebra there to find. You convert this source into phasor. Phasor would be equal to a 10 angle 10 degree. Then you solve for your voltage V. Then you convert it into time domain. You will get your VT, number one. I will not show this thing to you. This is the first year problem. Now, second thing is what? You consider your second source and whose phasor equal to what? 6 angle 35 degree. Now tell me, can we calculate this phasor and that phasor at same time?
No, sir.
The reason is
The frequency
frequency
is
is
not
different. As a result, the circuit will be different. Okay, because for this phasor, this capacitor is simply 1 divided by J2. But for this case, what will be the value?
set.
For this source, 1 divided by J6, exactly, because the frequencies are different. So from your phasor analysis, only applicable for a single frequency, not a combination of frequencies. So what you can do, you can calculate your DC component, you can calculate your output for your first term, you can calculate for your second term. Then you add them together, not in the phasor domain. You have to add them in the time domain, okay? Because if you add them in the phasor domain, then this complex term and that complex term will merge together. That will give you a meaningless something. For this reason, if your system contains multiple frequencies and alternating terms, what you need to do, if you want to apply phasor algebra there, you have to calculate by considering different frequency component differently. Then addition will be possible in the time domain, not in the phasor domain. So with this thing, this is a tiny example. You can calculate power, do it by yourself. Then in Fourier transform case, pick some problem from chapter 18 and try to solve it. I will also show one later, okay? But before going to that, let us make a relationship between Fourier transform and Fourier series. This is needed. And another issue is that we may have our system. That system may contain, your system can be an LTI, and your system can take a periodic input. Say we have our xt, that xt is periodic. But your hj omega of your system is continuous in frequency. That means if we have a transfer function that is continuous, but our input is a periodic function with discrete frequencies, then how to handle them? A mixed type situation. Although we have discussed the thing earlier. For example, in your class test, we have set a problem. That problem was what? That we said that we have a signal 100 e to the power minus 2t is period 0 to t to 2. And this signal is applied to a RC circuit with RC equal to 1 second, and find the magnitude of third harmonic. This was the problem. In this problem, didn't we find, for example, the earlier that because you need to find your hj omega. If you multiply your hj omega with your input Fourier transform, that will give you your yj omega. And in this case, first thing is what? You have to find your hj omega. That we illustrated several times, that for RC equal to 1, your hj omega equal to j omega plus 1. At harmonic frequencies, hj omega 0k, your transfer function would be equal to 1 j omega 0k plus 1. Then you multiply with this H0 with the Fourier constant of 100 e to the minus twice t. It is there in your example. You multiply them together and find its magnitude at k equal to 3. So if we have our, an example was also there in your book for the case of a square wave. Okay, if we have our Fourier series and Fourier transform, we have to relate them together. Then we have to start with the Fourier series representation of a periodic function first. So this is what the periodic Fourier series representation, exponential form obviously, of a periodic function, and xk is the Fourier constant. Now we know that if we have a 1, for example, a DC with magnitude equal to 1, its Fourier transform is this. Now, if we multiply our 1 with a term e to the power, say, j omega 0 kt, this is what? This multiplication in the time domain results in a frequency shift in the frequency domain. That you know that if we have a signal e to the power omega 0t multiplied by xt, your Fourier transform would be equal to what? Fourier transform would be equal to x j omega minus omega 0. This is what the Fourier transform. In our case, our xt equal to 1, whose Fourier transform is twice pi delta omega. Then if we multiply the signal with omega 0 kt, then what will happen? The Fourier transform will be equal to twice pi delta omega minus omega 0 k. And if we have a signal, for example, of this type, what is the difference between this and that? Only a factor, complex factor xk is multiplied. So if we multiply it with xk, then that xk will be coming here. This is for any value of k. So if we want to apply this thing in a for all the components of k, starting from k equal to minus infinity to infinity, this is what you signal. Your Fourier transform would be equal to what? Twice pi for each value of k, xk, and the corresponding shift of your delta function to the location of the harmonic. So this will be the Fourier transform of a periodic function. And here you see that xk is discrete with finite magnitude, but when we are taking in Fourier, they are taking the form of a continuous delta with amplitude approaching to infinity. But the number of delta will be equal to the number of xk. In the case of continuous time, that number is infinity theoretically from k equal to minus infinity to infinity. But in the case of discrete time periodic signal, we need only n numbers of Fourier constant that is equal to the period of your periodic signal. Okay, this is an example. Say, if we have a signal, something like this. This is actually an approximation of the square wave by using 3 or 4 harmonics. We will discuss another issue related to this type of, I will discuss it in the next class, inshallah. So this is our signal. If this signal has this Fourier transform, and this is periodic with period equal to t, then these are the Fourier coefficients that we obtain by integral. Now, if we want to take the Fourier transform, then what will happen? Each of your Fourier constant will be multiplied by an impulse, and your impulses will be appearing at integer multiple of k. So, if we have a DC term, that DC term will be associated with this one. Then your first harmonic term has this value of xk. The corresponding value will be equal to x1 into delta omega minus omega 0. The next value will be equal to x2 delta omega minus 2 omega 0, and so on. In either direction, this will be equal to x minus 1 delta omega plus 1. This is your x minus 2 delta omega plus 2. So in this way, we can find the Fourier transform of a discrete time signal. A discrete, continuous time periodic signal. In the same way, we can find that Fourier transform of a discrete time periodic signal. But the difference of Fourier constant between discrete time and continuous time is, for the discrete time cases, the Fourier coefficient will have a periodic nature in the frequency domain, because only n numbers of Fourier constant will be appearing after finite interval equal to the number of samples in one period of your original signal. This is the Fourier transform of cosine omega 0 t. Probably I have discussed the thing earlier. How many Fourier constants are present in cosine omega 0 t? In the exponential form?
2.
2. Then what are these two? At k equal to plus minus 1, isn't it? So you see that then how many terms will be there in Fourier series? We will have 2 terms there, okay? One is for k equal to plus 1, another is for k equal to minus 1. This is for k equal to minus 1, this is for k equal to 1. Magnitude equal to half. So your sum was equal to simply xk, originally xk delta omega minus k omega 0. But here in this case, you see that we have our 2 values of k, plus minus 1. So 2 terms will be there, in the 2 terms will be there. First for k equal to plus 1, another is for k equal to minus 1, amplitude of xk equal to half. So this was equal to twice pi multiplied by this. So this is what the spectrum appearing here. This is another spectrum appearing there. This is what the Fourier transform of a cosine wave. If we have a sine wave, what will be the Fourier transform? How many terms will be there in sine?
2 terms.
2 terms will be there in sine. If we have 2 terms, then a sum will be, but here in this case, in sine case, your coefficients are real. X minus 1 equal to half, x1 is also equal to half. But if it is sine omega 0t, x1 would be equal to what? By using Euler identity, is it not equal to 1 divided by 2j?
Yes, sir.
So that's it from my part. We have something left in compared with the other section because of the discussion that we made at the beginning. We will cover it in the next class, inshallah. So that's it from my part today. 35.
Yes, sir.